Hello everyone, good morning. I'm Hasin Rehana, a PhD student from University of North Dakota. Today I'm going to present our work on identifying cancer vaccine adjuvants in biomedical literature using large language models. The objective of our research is to automatically identify and extract adjuvant names from biomedical literature to support cancer vaccine research. Why it's important? It's important because adjuvants enhance the immune response and it is critical for vaccine effectiveness. Understanding which vaccines are used in existing cancer research can help us to accelerate the therapeutic discovery. However, manual curation is intensive and it's not scalable anymore due to the rapid growth of biomedical literature. So our goal is to accelerate the cancer vaccine research by enabling scalable, accurate extraction of adjuvant information from biomedical literature using large language models. So let's talk about a real scenario. Let's say a pandemic antigen is tested alongside three different adjuvants, adjuvant 1, adjuvant 2, and adjuvant 3. And let's say the researchers found that the adjuvant 2 with the antigen has the highest immune response. So they came up with a vaccine that has used the antigen and the adjuvant 2. And when they came up the vaccine, they have provided us with the literature, let's say the clinical trial information or the manuscript that mentions their result, their information that, okay, this adjuvant stimulate the antigen. And as biomedical curators, the curator's task is to extract those type of information from the existing literature. And here comes our model, which tries to extract the information automatically without the manual curators. So there are three adjuvant databases that has extensive information about the existing adjuvants. One is AdjuvaDB, which is a web-based compendium focused on candidate adjuvants used in different clinical settings. We have VaxJo, which is not only a database but also a analysis tool, and we also have Vaccine Adjuvant Compendium from NIH, which has the related clinical trials, the vaccine ontology, the articles related to the existing adjuvants. However, with the rapid growth of literature, it's hard to keep up. So there are a few challenges when identifying adjuvant names from the literature. One is biomedical texts often use technical and nuanced language, which is very hard to identify. And one adjuvant might have multiple names, might have different formulations depending on the clinical setting. Some terms can refer to both adjuvant and not adjuvant depending on the context. And also the manual review cannot keep up with the rapid growth of literature. So from biomedical literature to adjuvant knowledge curation, we have inputs in form of PubMed abstracts, clinical trials. We have the bottleneck of scalability with the complex language, contextual variability, and ambiguity. And we have different possible solutions. We have chosen LLM. And the final goal is to curate the adjuvant data and integrate them into the vaccine databases like VaxJo. So why we have chosen LLM? Because LLM brings together multiple unique strengths that make them ideal for transforming unstructured data into a structured, actionable data. They have the knowledge how they can handle the scientific language. They have context-aware extraction. It's not just keyword matching and extracting the keyword. It uses the context. It has the zero-shot and few-shot capabilities, which enables it to generalize and give us generalizable and scalable pipeline without actual fine-tuning or training. So there are two data sets we have used for this research. One is based on the PubMed abstract database, and the annotation source we have used for this is Vaccine Adjuvant Compendium. And the another one is mainly based on the clinical trial data sets, and the annotation was done by AdjuvaDB team. So this is the overall workflow of our adjuvant name recognition pipeline. We have taken the PubMed articles and the annotation from the vaccine database. We have also taken the clinical trials annotated by the Adjuvant DB, and we have done the basic pre-processing to feed them into the LLM pipeline. And then we have done extensive prompt engineering and came up with a structured, clear prompt that can help us with the inferencing. We have used two different LLM models. One is Llama 3.2 and another one is GPT-4o. And once we have the response, we have done the post-processings, and then we did automated evaluation as well as manual evaluation to see that how the adjuvant name recognition is working. So as for the context information, as LLM models are very aware of the context, we have tried to provide extra context to our prompt. We have tried to give substance information, which is the structured list of chemicals and biological entities from the PubMed records. And for the clinical trials, we have tried to provide the intervention information, which are basically the trial components which are administered to the participants. So these are some examples of substances, and these are some examples of interventions. And the purpose of this comparison is to see whether incorporating those structured context helps the LLMs to interface or not, and compare the performance with or without the additional context. And our hypothesis is context provides essential semantic grounding, which can reduce the false positives. So this is our prompt. We try to make it as structured as possible, and we have 4 different parts of this prompt. The first one is the task, that is, what is the actual task what the LLM has to do, and then we have provided some key instructions, the output format and the input format. So this is the base structure we have used, but we have tried different variations, and I'll show you the results later. But for now, let's see some sample outputs from LLM from both the Llama 3.2 and the GPT-4o. And you can see that the results are pretty structured. We need just basic tweaks, and then it will be ready for the automated evaluation, or let's say if we want to integrate it to a database. It's pretty standard. But let's break down some common errors. When you looked into the outputs manually, we have seen that in most cases, the errors occur due to the lack of standardization. Because the input we have used, the abstracts or the clinical trials, the vaccine adjuvant names are not standardized always. As a result, as we don't have the standardized input, the outputs are sometimes not standardized. For example, if we talk about an example, let's say a gold standard label is Adjuvants, which is a well-known adjuvant, but it has different synonyms. For example, delta inulin or delta inulin polysaccharide adjuvant. And let's say the LLM came up with the delta inulin polysaccharide adjuvant, which is actually true semantically, but it's not exactly what the gold standard was. As a result, when we have done the automated evaluation, it may say it's false positives, but it is actually true positive. So we have used both automated evaluation as well as manual evaluation to see how the LLM worked. And here is the comparative results on the back data set, on one of the data sets we have used, and you can see that you can see that the first the top curve is for the manual evaluation, and the lower curves are for the automated evaluation. And consistently, we have seen that for most of the parts, we have at least 10 to 15 or sometimes 20% increase in the score when we have done the manual evaluation. And we have tried 0-shot, 1-shot, 2-shot, 3-shot, and 4-shot prompting for all those. And we have seen that when we have provided some shots or examples to the model alongside the prompt, it has improved the performance. And we saw that GPT-4o, it outperforms Llama 3.2 in most cases, particularly in precision and F1 score. And Llama 3.2, it benefits more from the manual evaluation because it had more variable outputs, which helped when we tried the manual evaluation. And we can say that Llama 3.2, it shows higher recall, but its precision is smaller. And as I talk about the context information, like the intervention or substances. We saw that in most cases when we have provided those context information, although they do not have the adjuvant names exactly in the input, it is actually helping the models, and the performance is increasing with those extra context information. So to conclude, I'd like to say that large language models, obviously, it can effectively extract vaccine adjuvant names from the biomedical literature, although the literature is not very structured. And with structured prompts, sometimes they rival and sometimes even they have better performance than the state-of-the-art large language models like BioBird. And although we have those very promising results, I'd like to say that manual validation still remains essential if we want to come up with gold standard with the help of those LLMs. We still need the manpower in the pipeline, but it can definitely accelerate if we compare it with the whole manual process. So our future direction is that we want to extend the scope towards the infectious disease adjuvants. We want to start with targeted PubMed articles and clinical trials by pathogen classes. And also, once we have the pipeline ready, we want to incorporate the new findings into the Violin or VaxGeo to support the community accessible knowledge bases and accurate vaccine research. So I'd like to acknowledge the support from my mentors and the collaborators from my lab and the other collaborating labs, and also all my lab mates, and the support from NIH for helping us through the research. Thank you, everyone. If you have any question, I'm here, and you can also